Right, here we're going to talk about oxidative phosphorylation. Now, this is the process whereby we've got all this NADH, which we've made in the TCA cycle and a little bit in glycolysis. There's a lot of chemical energy in the NADH. We want to turn it into the oxidized form, NAD+, but there's not so much energy in that. And what's going to happen is all of that chemical energy is going to be converted into chemical energy of ATP. Okay, and it's been worked out that for every one NAD molecule, you get about one of those gives you about 2.5 ATPs. This all happens in the mitochondria. So let's have a think about how that actually happens. Now, before we do that, we just recall this little mnemonic, which you may remember from GCSE, oil rig, and this is about oxidation and reduction. And it's all to do with electrons, right? Oxidation is loss of electrons, reduction is gain of electrons. So we just remember that. Now, what happens in the mitochondria is, right, let's have a look at this here. The overall NAD, I'll do it red, NADH is oxidized by oxygen, and it forms NAD plus and H2O. And this is the final, this is the point where oxygen is needed for respiration. The NAD is going to lose electrons. It's going to give its electrons away, so it's going to become oxidized. And the oxygen is going to take hold of those electrons, and they're going to, okay, so the oxygen is going to be reduced to water. Now, if you just react oxygen with NAD like that, like I've done there in one go, it's pretty exothermic, and you waste all that chemical energy, will all be turned into heat energy, and we don't want to do that. We want to turn it into chemical energy of ATP, and this is what happens in the mitochondria. So let's have a little think. What happens in the mitochondria? You have something called an electron transport chain. Okay, so you start off with, on the top line here, these are all the reduced forms of these things, and on the bottom line, these are all the oxidized. So here's NAD, and it's reduced, and it gives away 2 electrons. So 2 electrons are transferred from NAD to this oxidized form of A. Of course, if you give electrons to that, it's going to become reduced form of A. And the reduced form of A passes those electrons on to the oxidized form of B, which in turn becomes the reduced form of B. And this carries on. I've only drawn, A and B and then water. There's actually an awful lot of them. But the final one that accepts the electrons is the oxygen. That's the final step. The electron transport chain is over, and the electrons are passed on to oxygen. You form water. Okay, so let's have a look at where this electron transport chain occurs. Right, that is a mitochondrion. I've drawn there, and it occurs. A mitochondria, they have 2 membranes. They have this inner membrane, and they have this one, the outer membrane. Now, the inner membrane is the site of oxidative phosphorylation. That's where the electron transport chain occurs. So this is called the matrix of the mitochondria in here. And you have your NADH molecules in there. Well, the NADH will pass the electrons, and they pass through various of these electron carriers which are in the inner membrane, and it ends up forming water, sorry. But when it does that, what it does is it pumps out, as the electrons are passed, it pumps electrons into this intermembrane space. So this gap between the blue and the black here, H+ ions are pumped out. So you create a concentration gradient where the H+ ions are more concentrated in the intermembrane space, and this is the intermembrane space here, than they are in the matrix. And that means they've got potential energy. And you can use that potential energy when they try and pass back into the matrix of the mitochondria. And when they do that, you can make them, use them to drive the synthesis of ATP. So that's it very briefly. Let's have a look in a little bit of detail. We don't need to know loads of detail, but right. So here I've drawn, this is my inner membrane. And this is the intermembrane space. And remember, what's going to happen when electron transfer occurs? You're going to do with a high concentration of H+ ions here. Right. So let's see. We start off with NADH here in the matrix, which is made in the TCA cycle and the Krebs cycle. NADH is going to pass on its electrons to see that pink thing there is a very big complex of proteins. Okay, there's lots of proteins in there. Proteins which contain iron atoms, and the iron atoms are very important for accepting the electrons. So it passes electrons on to this complex 1 here, and in doing so it will become NAD+, becomes oxidized. Now those electrons are then passed on to complex 2 via this molecule here called quinone, which you don't really need to know all the details of it, just call it Q. And then the electrons that the 2 will become reduced. 2 will then pass its electrons on to 3. 2 will become oxidized. 3 will become reduced. 3 goes on to cytochrome C, which is on the outside of the membrane actually. Cytochrome C becomes reduced, then it becomes oxidized. It passes electrons onto onto complex 4, and 4 finally passes those electrons on to the oxygen. So you've got half O2, and it goes to H2O. Now, at various stages in this, H+ ions are pumped out. So H+ ions are pumped out there. They're pumped out by that one, and they are pumped out in that place there as well. And this creates the proton gradient. So you end up with a high concentration of H+ ions. Then we've got this this complex here, this one in red. This is actually ATP. It's called ATP synthase. It makes ATP. And what happens is the protons, which you've got a high concentration of here, the hydrogen ions, they try and diffuse back in, and they diffuse back in through that. They can't get in through the rest of the inner membrane because this is very impermeable to H+ ions. It's very hydrophobic. The only way they can get back in is through these ATP synthase molecules, and when they do, ADP and inorganic phosphates are joined together to make ATP. So in that way, the chemical energy of the NADH is, via this proton gradient, ends up being transferred into chemical energy of ATP. It's not 100% efficient, so you will get some of it lost as heat, but it is pretty efficient. Let's just have a little think about how are these protons pumped? How on earth does this happen? Right. Well, you would not be asked this in the exam, but it's as well to have an appreciation of how it happens. Let's just take this molecule Q, which I've just talked about here. Okay, this, for example, now Q. Q will accept electrons. So electrons are passed on to Q and it gets reduced, 2e minus. That will turn it into Q 2e minus, 2 minus. It's double negative charge. So what that tends to do, it tends to recruit H+ ions from the matrix side. So we're going to get 2 H+ ions coming in here. 2 H+ coming in here, and that will form QH2. So we get QH2 there. Then when QH2 passes its electrons onto the next thing, right, it becomes Q again. So that, and there's the electrons. So it's got to release those H+ ions, and they get released like that onto the other side of the membrane. So it's very important the way that these electron transfer molecules, these carriers, are arranged in the membrane of the mitochondria so that they can pick up protons from this side and then let them go on the other side. Right. Now just have a quick talk about the yield and so forth here. Right, so each NAD molecule, I'll just rub some of this out. Okay. One NAD, that pumps 10 protons on average. And then when the protons are coming back in through the ATP synthase, so when they're coming in down here, you need 2.5 H plus ions to make 1 ATP. So that means each NAD, you can see, is going to give you, sorry, actually it's 4 protons there, beg your pardon. 4 protons make 1 ATP, so that means you're going to get 2.5 ATPs per NADH. Now you remember we were talking about FADH2 in one step of the TCA cycle, the citric acid cycle. One of the reduction steps, you didn't get NADH made, you get this other substance called FAD. You've got FADH2, that's the reduced form. Well, FADH2 actually gives its electrons into that part there, and it will turn into FAD. So that means it misses out. The electrons, when they come FAD, they miss out the complex 1. So that means with FAD, you don't get quite as many protons pumped through as you do with NAD. You only get 6 protons pumped, whereas with NAD, of course, you've got 10. Okay, this whole idea of using the electron transport chain to generate a gradient, this is called the chemiosmotic theory. Okay. Oh, finished.